All right, folks. So today we're looking at the first part of the Frost algorithm, the key generation. So there are 2 rounds, and each round, every participant will do some exchange of data. So let's begin with round 1. Round 1, every participant PI, so you are supposed to have n participants, and t is the threshold. So we do generate t random values, and each guy has generate these independently. So we have AI0 to AIT-1. So this is for user I, and you go from 0 to t-1. So you do have t parameters, and they all have to be random. The Q here is a large value, just saying that it's an integer between 0 and q-1. Okay, and then you take these random values and you form this polynomial of degree t-1. So as a refresher, the a polynomial is something that has this form. So a0 a plus bx plus cx squared plus dx cubed and so on. So basically each value that you pick at random becomes one coefficient of this polynomial. Okay. So nothing very difficult so far. So now every P1 compute a proof of knowledge to the corresponding secret AI0. So the secret is your first term. And I'm going to guess that the rest of the terms will be for computing the shares. The fact that you have t shares, t random values, seems to indicate that we are going to use Shamir shared secret. Okay, so you calculate Ri mu I, such as k is pick at random. K is pick at random? Where's k? Where's k? Okay, so they don't mention k, but I'm going to say that k is a random value. And G is the generator of your curve. So you take key A as K as an ephemeral secret, and you derive the public key matching K by multiplying by G. And now you hash I, which is your index, phi, which is some string. So phi is in any string that you will change every time, so that this hash will change on every signature, even if other stuff are the same. It prevents people from repeating your signature and repeating the same process and replaying that as a new round. So phi and then J of AI0. So that's your public key. And Ri. Okay, so this is actually the same as Schnorr, right? So we saw Schnorr before, and this is exactly the same as a Schnorr signature. And knowing that you have big K as a secret. I don't know if we mentioned Schnorr last time. And that would, let me see if I mentioned Schnorr in this video. I don't think I did introduce Schnorr, but this is actually Schnorr. So this is a signature. Well, basically, you're signing phi as your message. Okay. We can take a look at this algorithm later, especially when we do the verification, signing and verification of Schnorr. Okay, so doing that means that the guy who receives this stuff, so this is our signature. He can verify that indeed you know AI0 if we agree on AIJ, which probably would come just afterwards. Okay. Then step 3. So you have computed this, right? You have computed sigma I. And then every participant PI computes a public commitment CI, which is then a vector, because each term of that vector is these coefficient multiplied by G. Or they raise the power, but I prefer to call it multiplication. It's basically the same thing. So that means that this term here is going to be the public key that matches our AI0. So that signature sigma I is a signature for that public key and that message sigma. Okay, so step 4, we send this commitment vector as well as the digital signatures. This is a vector, so it has many terms, and sigma I is just the signature on the first term. Okay, upon receiving CL and sigma L from participants, so everybody broadcasts to everyone. So every participant receives n-1 of these guys. So you are going to verify now that what you have received is valid. Okay, so we just need to verify that sigma L, so the signature of somebody else, verify this guy, and mu L, yeah, mu L is this term, right? This is your signature, but checking this. Okay, so this is exactly the verification algorithm for Schnorr. Okay, and then when this okay, we can forget about the signature. So signature was just to ensure that this commitment vector that the user knows about that secret. Okay, round 2 now. So end of round 1, basically everybody has created his own vector of secret value. So there's one secret, and then there's a bunch of extra coefficients. So each guy has one secret, and he has committed to that vector of coefficients by submitting public keys that correspond to these coefficients. So, and that has been verified by the recipients. Now in round 2, each participant securely sent to each other a secret share. All right, so now the secret share is L, FIL. Okay, so this is the evaluation of this polynomial. What is it? Here, this polynomial at values 1, 2, 3, 4, 5, and etc. And so that's your share. So you're gonna receive. Okay, so there are n polynomials because each participant has a polynomial, and for each polynomial there are n shares. Except that your own share is probably useless. Yeah, there's your own share, which is I and FI, so the diagonal. You don't submit to other people. So you can imagine this is like a matrix of values. So Fi is several functions, and then for each Fi you have evaluation at n points. So it's n by n. Okay, now each PI verifies their share by calculating GFI. So that's actually a fairly common trick. You verify that your share is correct by evaluating the same polynomial, so g power fi, because you have the public keys that match each coefficient. Okay, so this stands because of the linearity of the polynomial. We can go in details in a later video and check. We will check all the math in the later video, but so far it's not super surprising. We can see kind of intuitively why this works. Okay, and then part 3, each PI calculates their long-lived private signing share by computing. Oh, so now you sum for your given index, right? So you assign a index or the x value on the 1, 2, 3, 4, right? And then you sum each of the polynomial fi evaluated at your particular index, x equal I. And that is going to be your final share. Right, so then once you have summed them all together, you don't need to keep the individual parts. So then you store this value and then you throw away the FL, the I. Okay. And now, so that's your share of the secret. But the trick here, of course, is that nobody has the secret. But we will still be able, everybody's still able to derive the public value that corresponds to that secret public group secret. Each participant calculates their public verification share. Okay, so that's where we are. By just multiplying that secret by SI. Okay, that's fine. So these terms, I don't really know why we need that. Maybe later. And the group public key is the product of, or what's the product here? But essentially, since we're using summation for the group law, this is same as saying that the secret is the sum. Okay, so the implied secret is that it's going to be the sum of all these AI zeros, right? So you're choosing, each participant has chosen this term as their secret share, and then the group secret is going to be the sum of all these guys. Therefore, the public group, the group public key, is going to be the sum of these guys. Right, so they write it as multiplication, but that's just a matter of convention. So that's there. And also, any participant can compute the public verification share of any other participant. Okay, so me, not only I have access to my own public share, but I have access to the other people verification share. So, and that's because of what? It's the product. Yi is, oh yeah. So because I can evaluate, I have received I have received this stuff from the other guys, so I also can calculate it from the other people, right? But I'm not sure it's used anywhere else, because at this point, what we need to know is this guy, this Y, because then we can derive the address based on the public key. So the address where people who can send us money, send money to the group, and then the private signing shares of each participant will be used to produce the signature. So at this point, I don't know why we need this guy or this guy. but probably later. All right, so that is not too bad, right? We figured out what's the algorithm for doing the keygen. What we can see is that every participant contributes equally because they each have to choose their own term here. And the group secret is simply the sum of all these individual secrets. And the commitment here is used so that if a guy pretends to have he's not cooperating with the protocol and he fakes the knowledge of this, then he will be caught by not being able to provide the proper commitment. So he has an additional part where he has to prove that the vector that he gives here is indeed, he knows indeed that term. Okay, so next video we'll see how we actually generate the signature. Okay, so another thing is we probably, if we want to go deeper, there are a few things that we could cover. One is this whole story about polynomial here. So how does this actually work? And a part about the generation of the Schnorr signature. And I think that's pretty much it for this part. Okay, so pretty short all in all. All right, folks, that's it.